Hello everyone, this is Gautami from Sri Venkateshwara College of Engineering. Today we'll talk about the subject called discrete mathematical structure. In that we'll be seeing a topic called additive group of integer. So we'll move on to the introduction part. Additive group of integer modulo n. Modular arithmetic is a fundamental concept in mathematics where numbers are represented in the term of the remainder when divided by a fixed integer known as modulus. The additive group of integer modulo n is a powerful algebraic structure that plays a crucial role in various areas of mathematical and computer science. In this additive group, we'll be taking only the remainder part. Whatever the number we will be dividing, we'll be considering the remainder part, but not the quotient or the divisor. Additive group of integer modulo n. Definition. The additive group of integer modulo n denoted by z divided by nz plus. Here z plus indicates the positive integers. Is a set of all equivalence classes of integers under the equivalence relation of congruence modulo n. Elements. The elements of this group are the integers 0, 1, 2, so on until n minus 1, where each integer is represented by its remainder when divided by n. Group operation. The group operation is an addition where the sum of two elements is calculated by adding the corresponding integer and taking the remainder, then dividing by the n. So this group operation will be represented in a form of a table where we'll be multiplying the column number with the row number, and then if it exceeds the given number, then we'll be not even if exceeds, we will be adding it, and then we'll be dividing it with the given total number to get the modulo of the number. Properties are of the additive group. Closure property. The additive group of integer modulo n is closed under the operation of additive, meaning that the sum of all two elements in the group is also an element in the group. For example, let us consider the element A and B, which belongs to group A. And then now if I take an element A plus B, that number should also belongs to the particular group A. For example, if I consider that positive integer is a set of group G, and then I'll take A and B as 1 and 2. So now 1 and 2 belongs to the group G. And if I add 1 plus 2, that is 3, 3 also belongs to the group G. So this will satisfy the closure property. Associative property. Additionally, in the additive group of integer modulo n is associative, which means that the order of addition does not affect the result. So it can be like if there is a three numbers, you can first add AB and then later add the result with C, or else you can add BC, later add the result with A. The result will not change, however the addition is done. Existence of inverse. Every element in an additive group of integer modulo n has an additive inverse, which is the element that when added to the original element result is the identity element. So every element which exists in that particular group will be having an inverse of that element. The inverse will be finding the inverse on the basis of the identity element. Identity element is nothing but when you add a number, that is when you add an identity number with the element, you will get the element itself. For example, if you take 1, the identity element for this additive group is 0. If you add 1 plus 0, the answer will be 1, which is the same as the original number. In the case of getting an inverse, we have to show that when we add two numbers, we get the answer as 0. That is, we get the answer as the additive element. Congruence and equivalence classes. Congruence relation. Two integers A and B are said to be congruent modulo n if they have the same remainder when divided by n. So the congruence relation is said to be that when there are two integers and you divide it by some number and you get the same remainder for both the number. Equivalence classes. Equivalence classes of integer under the congruence relation modulo n are the set of all integer with the same remainder divided by n. Representation. Each equivalence classes can be represented by any one of its element, which are the integer 0, 1 up to n minus 1. So we'll see an example over here. We say integers A and B are congruent modulo n if there is a difference in multiplication of m. For a group, 17 and 15 are congruent. Modulo 3, because when I do 17 minus 5, I get 12, and which is nearly equal to when I multiply it by 4 into 3, also I get 12. And the next number we are taking is 184 and 51. The congruent modulo 19. So since when we minus it, we get that 133. And then when we do the remainder of it, we get the same one. In the same way, a familiar usage of modular arithmetic is whenever we convert between the 12 and 24-hour clause. We know that 14 hour is to the 2 hour PM indicates the same time, since 14 is equivalent to 2 modulo 4. So this is nothing but there can be two numbers which can be represented in a different way, but it means the same when it is divided by the modulo in the case of additive group. Although used less commonly, we can extend this definition to rational numbers. The rational numbers 1 by 2 and 13 by 2 are the congruent modulo 3, because when I minus both, I get 6, and when I take the remainders of the both, I get the same value. So this is another example where it is representation of both the additive and multiplication. Now for this video, we'll be concentrating on only additive group. So now we are considering that Z5. The Z5 indicates the number of elements which will be present in this group. So as we can see that we'll be starting with 0 in the additive group, and we'll be ending unto the n-1, that is 4. So as we can see that here, we are representing all the row from 0 to 4 and even the column from 0 to 4. So we are indicating this plus, this says that this is an additive group. So now we'll be first adding the number, and later we'll be doing the modulus of that number with 5, because that is Z5. That indicates that there are 5 elements and you're supposed to do modulo with 5. So here we're taking an example, that is 0 plus 0 is 0, and if you do the modulo of 0, you get the answer 0. 0 plus 1 is 1, modulo of 1 is 1, and 0 plus 2 is 2, modulo of 2 is 2. In the same way, if we continue, we'll go to another example, where 1 plus 3 is 4 and 4 modulo of 5 is 4. But 1 plus 5 is 5 and the modulus of 5 is 0. In the same way, when we go further, we'll go to some greater number, that is 4 plus 4, which is 8, modulo of 5. We get 3. So that is 3 over here. So in the same way, this is taken for each and every box of the table. So now we'll satisfy all the 3 properties. There is a closure property, an associative property, identity element will find, and we'll find the inverse of it. So in this example, we can see that for the closure property, I can say that from this table, whenever I added the rows and the column, I got the same number. There were no different number forming in the table. So according to this, I can say that the closure property is satisfied. Next, coming to the associate property, let us take an example that the elements are 0 and 1 and 2. So when I add 0 plus 1, later add with 2, I get 0 plus 1 is 1, later added with 2, I get as 3. Or else, if I do it in an inverse way, that is 2 plus 1 first, that is 3, again plus 0 is 0, 3. So both the answers are 3, so there is no difference in the result, and the associative property satisfies this. And then we'll be going to find the identity element. It is very simple and easy to find identity element, because whenever the element will be multiplied with that element, identical element, we get the same number. So in this table, we can easily observe that the elements which we are given as 0, 1, 2, 3, 4. And whenever we had added with 0, we got the same element, that is 0, 1, 2, 3, 4 for the respective numbers. So the identity element in this additional group, we can say that it is 0. It is not necessary that it always needs to be 0. If there is any number which is, for example, multiplication, we get identity element as 1. And for example, if in additive group itself, if you take any numbers, and then maybe the E represents the identical element over there. So it differs from the sum to sum. So then we comes to the inverse. So as we have already found the identity element is 0, it is very easier for us to find the inverse. For example, let us find the inverse of 2. What will be the inverse of 2? To find this, just go through the row of the 2 and find where is the 0. After locating where is 0, go to the upper column 3. So we can see that the 2 inverse is 3. So in this way, we can find the inverse of every element using the table. Additive inverse at identity element. Additive inverse. In the additive group of integer modulo n, the additive inverse of an element A is an element minus A modulo n. That can be said as A inverse, which when added to A results in an identity element. Identity element. The identity element in the additive group of integer modulo n is the equivalence class containing the integer 0, as adding 0 to an element in the group does not change the element. As we had discussed in the earlier, that is, additive inverse can be represented with the help of an A inverse. That is, A plus A inverse gives the additive element, that is 0. In the same way, identity element. When whatever element you consider 1112. So when you add 1200 with the 0, you get the same answer, that is 1200. So whatever the number may be, when it is added in the additive group, we get the same number itself. It differs from the multiplication by saying that when there is a number and it is multiplied by an additive element and identity element, we'll get the same element. For example, in multiplication, the identity element is 1. So in this, we can see it is a tabular representation of how it has been done. Illustration of this. Arithmetic operation in additive group. So what are the arithmetic operations can be done? We can be doing addition. Addition in additive group of integer modulo n follows the same rule as an regular integer addition, but the result is reduced by modulo n. Subtraction. Subtraction in the additive group of integer modulo n is the same as adding the additive inverse of a subtrahend. Negation. The negation of an element in an additive group of integer modulo n is its additive inverse. So these are the extra arithmetical operation which can be done in additional additive group. So, but we always follow the additive group as the addition operation, where we supposed to or it satisfy all the three properties, that is closure property, associative property. We can find the identity element and also the inverse element of each element. So in this, we can see that definition A modulo n means the remainder when A is divided by n. So the application, where are the application where we'll be using identity group and how it is useful. Cryptography, the identity additive group of an integer modulo n is a fundamental in development of cryptography algorithm such as RSA error correction codes. Modular arithmetic is used in the construction of error correcting codes, which are crucial for reliable data transmission and storage. Computer science. Modular arithmetic is used in various areas of computer science, including the hash functions, pseudo-random number generation, and finite find arithmetics. So we can see that it is mostly in the data structure part, and also the areas where you're using arithmetic, statistics, and all additive groups comes into the role. So conclusion and the key. Fundamental concepts. We studied about the additive group of integer modulo n as a fundamental concept in mathematics with numerous application in various fields. Algebraic structure. This group possesses the important algebraic properties such as closure, associative, and existence of additive inverse. We also saw how we are supposed to prove it with an example. Practical significance. The additive group of integer modulo n has a significant practical application in the areas like cryptography, error correction, and computer science. So in this video, we saw what was the additive group. We saw this definition, we saw the statements, we saw the properties of it, and we tried to proving it with taking an example of a sum, and we concluded with knowing the applications part. So this was all about the video. I hope it was helpful. If so, please do like the video. Thank you for watching it.